Next problem, we have two small metallic spheres, each of a mass 0.2 grams. And they are suspended by pendulums, or they're as pendulums by light strings with a common point, right? So this is in the book. I definitely recommend you checking out the book because it makes things a little more clear. So they're given some electric charge, and it is found that they come to equilibrium. So here they are standing in equilibrium. The angle here is 5 degrees from the vertical. Here is 5 degrees. Okay? Each string, L, is 30 centimeters. And then we need to find the charge. So we want to know Q on each sphere. Okay? So, first thing we need to do is set up a force diagram. So we have an electric force. Let's list our forces, right? We have an electric force. If we just pick one of the spheres, we're going to have a force between them pushing this way, right? If they're the same charge. Okay? So that's one. The next one is going to be a tensile force. You could also say that the electric force is pushing this way. It would be the same. So we have a tensile force. So here would be Ft tensile, Fe electric, and then we have the ball. One of the spheres will be hanging its weight force, right? So since it's in equilibrium, we have 0 is equal to Ft plus F weight force plus F electric force. So then, we also need to break these down into x and y components because we have y component this way and an x component this way, right? So for y components, we have weight force, and then there's a component of the tensile force. For the x component, we have the electric force and a component of the tensile force. So let's break these down into the x. So the sum of the x components is going to be the electric plus the tensile in the x direction. This is going to be equal to 0 because we're in equilibrium. So that means that this is equal to F negative x component of the tensile force. Now recall that a tension force is going to be the magnitude of, it's going to be, okay, so if we want the component, it's going to be the magnitude of the force, and then sine of, since we're asking for the x direction, it's sine of the angle, because this is also 5 degrees. Okay, so that gives us negative Ft sine of 5 degrees. Right? So that's where we're going to leave that for now. This is, because I want to go back to the y component for a second. So let's do the y component first. We'll come back to this one in a second. So we have Ft. Now we're doing the y component of the tension force, cosine of 5 degrees. And then it's going to be minus mg. So if we look at our diagram again, we'll see what we mean here. We have the tension is actually pulling this way. So this blue thing should be facing that way, right? The weight force is pulling down. So we have positive tension force, negative weight force. Okay, again, these are equal to 0. So now we can find the magnitude of the tension force. Why I stopped this one up here and we're going to come back to it is because, well, we have two unknowns here in one equation, so we can't really do much with that yet. But if we come to this one, we have mg over cosine 5 degrees is equal to the magnitude of the tension force. That's what we just got. So now we can go back to our other equation and plug that in. So now we're going back to this one and plugging this in. Cosine 5 degrees times sine 5 degrees. This is the magnitude of the electric force, so it's mg tangent 5 degrees. Okay. So now we want to find the charge using Coulomb's force law. Right? What is the distance between them? So the distance between the two spheres is going to be L sine theta. This is L sine theta here. Here's L, here's theta. So this distance is L sine theta. But between the two of them, it's 2 L sine theta. That's our distance. So now if we set this up as a force law, our electric force as we know it, charge 1, charge 2, well, we know that they're the same. So we'll just say charge squared, right, over r squared is equal to k. Charge squared over 2L sine 5 degrees squared. Now we set that equal to our electric force up here, which is equal to mg tangent theta. And then we solve for Q. Okay, so what does that give us? 2L sine 5 degrees squared times mg tangent 5 degrees over k. Just double checking my work here. And then this is all, sorry, this is not a negative. I don't know why this negative is here. This is all under a, so then we solve for the Q, right? And that should be what we get. So we plug all this in, which I have done, and then we end up with 7.199 nanocoulombs, or 7.2 nanocoulombs. So that's problem 15.